Second, I am going to share you the screen. Okay, can you see the screen? Good. Indeed. You know that, okay, any polynomial in one variable can be written in this form. We call them univariate polynomials. And indeed, we have a field D, which is either, we call it D of X, and this D can either be Z, set of integers, Q, set of rationals, or set of reals, or C, set of complex numbers. In general, we call polynomial a function, and you know that AIXI is called the ith term of the polynomial, and AI is called the coefficient. When we say that two polynomials are equal or identical, we write this or maybe this if all the corresponding coefficients be identical. We know about the zeros of polynomial. We call ANXN the leading term and AN the leading coefficient. If we have two different polynomials, it is easy to define sum of them or the product, which would be a polynomial of degree n plus m, and ci, I mean the coefficient of xi, would be the sum of terms of the form AR BS when R plus S is I, that is, it can be written in this form. Okay?
Yes, sir.
The degree of f plus g would be less than or equal to the max of degree of f and g. And the degree of fg is indeed the sum of deg of f and deg of g. In general, fg can be written in this form plus the sum of lower terms, and n plus m would be equal to the sum of the deg of f plus deg of g. We have an important thing about division of polynomials. We say that f is divisible by g if there is some h satisfying this. And we write g divides f, or we call g is a factor of f and f as a multiple of g. If such h doesn't exist, so g doesn't divide f, and we use this notation. So again, something very similar to divisibility in number theory holds here. If g divides h and h divides f, we have this. If g divides f and h, it divides all the combination of f and g. And if g divides f, then either f is 0 or deg of g is less than or equal to deg of f. In addition, if g divides f and f divides g, this means that f and g are proportional. But what is more important is here. When we have f and g here and g is non-zero, then we can divide f by g. There would be unique polynomials q and r satisfying this. The quotient q and the remainder r are uniquely be determined, satisfying this also. This is so important, that deg of r is less than deg of g. The proof is easy indeed. We can do this something like by induction. Assume that n is deg of f, m is deg of g. So denote q1 as this. So consider f1 as f minus q1 times g. So it is easy to find that either f1 is 0 or deg of f1 is less than deg of f. So if f1 is not 0 and we have this, we can use something like induction hypothesis for f1 instead of f. And every time we can repeat this procedure to finally find this. But there is no need to prove this important fact, but just remember this important fact. Okay. Any questions so far? Something important is here. That, for example, if f and g are in z of x, and the leading coefficient of g is plus or minus 1, this division algorithm show that q and r would also have integer coefficients. This is very important. On the other hand, if we have this, then q and r would also go to q of x. But if we have f and g in z of x, but the leading coefficient of g is not plus or minus 1, then q and r would have rational coefficients. Okay? Moreover, let f and g be two polynomials in some field, f of x. Both are not 0 if we define this set as f times alpha plus g times beta for a and alpha and beta in f. Then very similar to the greatest common divisor, there exists a unique polynomial d of x with leading coefficients 1, such that d exactly divides all the polynomials in S. Obviously, let d of x be one of the polynomials with the lowest degree, and we can assume that the leading coefficient is 1. We will prove this. Indeed, the argument is very similar to what we did by the time that you had been learning greatest common divisor. So if we consider the term of the lowest degree here, and we denote it by d, we prove that d divides all the elements of this set. Indeed, let f be a member of S. Indeed, f can be divide f by d. So indeed, r is either 0 or deg of r is less than deg of d. If r is 0, we are done. Otherwise, because d is in S, d times q is in S, f is in S, so their difference would be a member of S, but the degree of r is less than degree of d. So this is a contradiction. For the proof of the uniqueness, assume that, okay, we have some D1, okay, we have this. So since both of them are monic, D and D1 are equal. Any question, guys? No. If we put alpha 1, beta 0, then we find that D divides F. By the same token, D divides G. So D is a common factor of F and G. On the other hand, since D is in S, there are alpha and beta satisfying this. Therefore, if D1 is any common factor of F and G, D1 divides D. So deg of D1 is less than or equal to deg of D. Therefore, D of X is unique common factor of F and G with the highest degree. We deduce it, indeed, we define it as the greatest common factor of F and G and writing it as this. Is it okay? Moreover, if F and G have no common factor, we call them coprime. And indeed, since we know that according what we proved, there are alpha and beta satisfying this. If they are coprime, we have this. And this is Bezout identity, indeed analogous to Bezout identity in number theory. So again, several number theoretic things happens. If F and H are coprime, G and H are coprime, FG and H would be coprime. If G divides FH and G and H are coprime, then G divides F, blah, blah, blah. And moreover, if F and G have rational coefficients, then D of X would also have rational coefficient. This is important because, again, in that field, there are alpha and beta in Q of X satisfying this. So if we have two polynomials with rational coefficients, their GCD would also have rational coefficients. Is it okay?
Yes, sir.
Finally, we have some definition about irreducible polynomials and unique factorization. By irreducible polynomial, which is similar to prime numbers over F. So for any irreducibility, we need a field. We mean a polynomial which cannot be factored anymore. This is very similar to prime number. And in the field of polynomials, we also have unique factorization. Finally, we have something about polynomials modulo a prime. If the coefficients of the corresponding terms of two polynomials f and g are all congruent to each other mod p, then we say that f and g are congruent mod p, and we write this. If the coefficients of p of f is not divisible by p, then the highest power in which the coefficients are not divisible by p is called the degree. For example, consider this polynomial, mod 5, the degree is 3, because this would be 0. And mod 2, the degree is 0, because both this and this are divisible. So congruency of polynomials is also very similar to congruency of numbers. You can see that every polynomial is congruent to itself. We have this, blah, blah, blah. Okay.
Sir.
So let us solve some example. First, find all polynomials with real coefficients such that f of x2 is equal to f2 of x. Indeed, okay, we rewrite a general case for f, and we are going to prove that an minus 1 up to a0 are 0. Suppose that ai for some I here are not all 0, and let k less than n be the largest subscript such that ak is not 0. From this, we find that, okay, on the left, f of x2 would be this. And on the right, we have this. Any objection?
No, sir.
Okay. Now, if we compare the coefficient of xn plus k on both sides, on the right side, it would be 2 times an ak. On the left, it would be 0 because n plus k would be between 2n and 2k, but there isn't any term between an and ak. So this must be 0 since an is not 0 and ak is not 0. This is a contradiction. So our initial assumption was wrong, and all the coefficients from here up to here are 0. So f is this. Plugging here, we find that an is 1 and f is xn. So this was an easy problem concerning finding the polynomials. Any question, guys?
No, sir.
Okay. Now think about this example. Let n is greater than or 0. Prove that the polynomial this is divisible by this. Okay? You would have 10 minutes. Okay? So start working.
Okay, sir.
Okay. Are you going back? I think you had some internet problem, right?
Others are trying to join, sir.
Okay, okay. Did you solve the problem?
Sir, I'm still working on it.
Okay. We will wait for 5 minutes until your friends will join. Then we will continue. Okay, guys. Can you hear me?
Yes, sir.
Okay, okay. Let us work on this problem. Indeed, we should say that, okay, this divides this, right? So there are two approaches for that. First is what you can see here, induction. Indeed, the base would be clear. It would be x2 plus x plus 1. So it is clear. So assume that the conclusion holds for n minus 1. That is, this is divisible by this, okay? No, we are going to prove that this is also divisible by this, right? So, can you hear me?
Yes, sir.
Okay. In doing so, I am going to do something. Try to relate this and this. So indeed, we rewrite this in this form plus this. And then we break this into this and x times this. So of course, this is divisible by x2 plus x plus 1. And according to induction hypothesis, this is also divisible by x2 plus x plus 1. So we are done, right?
Yes, sir.
Okay, so this is one approach. Let me also generate another approach. So wait a second. Wait a second. Okay. Can you see?
Yes, sir.
So we are going to prove that x plus y to the power of 2n plus 2 plus xn plus 1 xn plus 2 is divisible by x2 plus x plus 1, right? We need to prove this. Okay. So we consider this mode.
Excuse me, sir.
Ha ha ha.
Sir, wouldn't it be x plus 1 raised to the power 2n plus 1?
Yeah, we can do this, or we can do this. We can rewrite it in this form. X plus 1 to the power of 2 to the power of n plus 1, okay? Oh, sorry. Yeah, you are right. This is 2n plus 1. No problem. No problem. Thank you. Indeed, x plus 1 would be congruent to minus x2 mod x2 plus x plus 1. Do you agree? Do you agree?
Yes, sir.
Okay, so this expression would be congruent to this minus x2 to the power of 2n plus 1 plus x to the power of n plus 2, right? Okay, so this can be written in this form. You can factor xn plus 2, then what will remain is this 1 minus x to the power of 3n, right? Do you agree? This minus sign would persist. 2 times 2n plus 1 would be 4n plus 2. Factoring n plus 2, we will have 3n, right?
Yes, sir. Yes, sir.
So Look at here. This is divisible by x cube minus 1. Do you agree?
Yes, sir.
And x cube minus 1 is divisible by this. So we are done. Correct?
Yes, sir.
Very good. Very good. Any question?
No, sir.
Okay. Okay. Now, work on this example. Let f of x be this. Prove that for any positive integer n, f of x to the power of n has at least one negative coefficient. Okay? So think about it. You will have 10 minutes. When would we guys, when would be your national Olympiad?
Sir, 29 June.
So you have time.
Yes, sir.
One question. When would be your do you know? Your Maghreb pray.
Sir, it's on 7 o'clock.
When?
7 o'clock.
7 o'clock. So in 8 minutes, right?
Yes, sir.
Okay.
Should we
So let us
start?
solve.
We have our dinner after the Maghrib prayer.
Okay. So let me finish this problem. Then you can go for pray and dinner. Indeed, we calculate the coefficient of x cubed in fn of x. Indeed, fn of x would be the product of these brackets, correct? So
Yes, sir.
x cubed terms from the expansion can be generated in two ways. One is that x cubed term in one of factors and the right side above multiplied by constant terms of other factors, which, okay, in n ways we can choose that x cubed, and from the others we would have two. Okay? On the other hand, we can generate x cubed as the product of x2 and x. Okay, we have x2, we have x. So, indeed, in n way, we can choose x2. In n minus 1 way, we can choose x. So, the coefficient of x cubed in general would be this times this minus this times this, and the rest constant terms. And this can be written in this form. So of course, for all n greater than or equal to 2, it is negative. And for n equals 1, everything is clear. We can also see that, okay, the coefficient of x2 is also this. So this cannot work. So x cubed was the best choice that we had. Any question, guys? No?
No, sir.
Okay. This was a good problem indeed. So you have some exercises, homeworks, let's say. Take a picture from this. You should work on this until tomorrow. Homework 1. Determine which of the polynomials this and this has a larger coefficient in x20. Okay, so this is homework 1. Homework 2. Find all positive integers k such that this is divisible by this. So again, you can rewrite xk as minus x minus 1. Then try to use this here in order to generate something meaningful. And finally, the hardest one is this one. So take a photo from these three. This is homework 3. For non-negative integers m and n, denote by a, m, and n the coefficient of xn